excuse me, third and final video is going to be our last problem, problem 4. Right, so you find the flux of f of xyz, where that function is xi plus 2yj plus 3zk, where s is oriented outward, and the cube with vertices positive and negative 1, positive, negative 1, positive, negative 1. So kind of drawing this thing, at least trying to sketch it. So it looks like we're going to have, let's see, we'll put a point here. That's x is positive 1, x is negative 1 is going to be back here somewhere. Y is positive 1, y is negative 1, back here. And then z is positive 1, z is negative 1, down here somewhere. It looks like we're going to have something that kind of looks like this. Let's see how well I can draw this, see how parallel I stayed. Yeah. Not the best, but it'll do. Oh, it's not horrible. It's not great. Oops, forgot the front of the cube here. And then the back of the cube. Ooh, that one was not good. Let's try that again. Yeah, a little bit better. Um, Actually, it doesn't really look all that great. It's supposed to go out more this way, away from the y-axis. Where is my xy axis? I don't know. Kind of hard to tell from this, but here, I don't really like that. Let's try again, because we can. So, let's see, it should go out this way, out this way, out this way, out this way, and it should be from the hardest part here is to get the depth of this thing right. Alright, well, it's slightly better. What you have to imagine is that this point right here is kind of someplace right in the center of this, and this, I did not draw this very well. It's supposed to be a cube. The height should be much bigger. We'll just have to do some imagining because I don't want to draw it again. But here's the idea. So what we have is, we have 6 faces of this thing. So this outside piece, the one that's facing the most down the x-axis, we'll call S1. I'll call the back face, so that one right there, we'll call that S2. Try and do this in some different colors so that we can get somewhat of a sense of what's going on. S3 will be the side face here. So this is the one in the most Y direction. And then S4, so this was S3. S4 will be the side face, which is most in the Y direction to the negative. And then we'll go with some blue here and represent the Z, which is going to be the top and the bottom. So let's see if I can label that. So right up on the top is going to be S5, and then down here at the bottom, so the one coming down there at the bottom is going to be S6, which will represent the top here and then the bottom. So we've got 6 different faces, and what we want is we want outward flow. So everything's going to be coming out of the box in 6 different directions. So we've got flow going up, flow going down, flow going left, right, in every direction. So let's see what we've got. We've got 6 faces. And you might be thinking, wow, that's a lot of these things to do, and it is, but this should actually go pretty quickly. We'll see how this goes. So the first one we'll call S1. And S1 is we want the flow to be in the positive x direction. So we're going to have the positive x direction. We want the flow coming out this direction right here. Oops. So let's see how we're going to parameterize this thing. So x is always 1 according to this, right? This whole face, x is 1. So I think we're just going to go with a trivial parameterization here, say y is y and z is z. Because of the fact that x is 1, we have now an r which is in 2 variables. So we're going to need r sub y. Well, the derivative of this stuff with respect to y is 0, 1, 0. Okay, not too bad there. The derivative of this with respect to z is 0, 0, 1. So it looks like our normal vector, which is the cross of these two, if we cross these two, let's see, that's going to give me 1 minus 0, so that's 1. Everything else is going to be 0, because this will be 0 minus 0, 0 minus 0. Yep, so we're going to get 0, 0. Okay, and that's the cross of those. This is positive 1, which is good. It is outwardly oriented. If I had accidentally, excuse me, done r of z on top of this thing, we would have gotten negative 1, which would really just indicate S2 in this case. So again, we'll already know kind of what S2 is going to be. Now that we have n, we're going to need to write down f. This is our function f up here, which remember is really just x, 2y, 3z. But in this case, x is 1 constantly, so our f is 1, comma 2y, comma 3z. And then we'll have to dot these two things right here. If we dot them, f dot n, I'm going to get 1, 0, 0. So I'm going to get 1. Okay, that's really nice. We'll do all the integration of all these things later. S2, we want to be in the negative x direction. It's this face, so outwardly oriented is in the negative x direction. So we want that to be in our negative x direction. Again, we're going to go with the trivial parameterization. We don't really need to write this stuff down. The only thing that's going to change is that x is negative 1. Y is still y, z is still z. So when you get your normal vector, and I just mentioned it, if we flip these two things around, because they're going to be exactly the same, ry and rz, our normal vector is now going to be negative 1, 0, 0, which is what we want. We want the normal vector to be pushing out in the negative x direction. And then we'll do f dot n. It's the same f, except now this is a negative 1 here. So we'll put that in there. F is negative 1, 2y, oops, 3z. And then f dot n is going to be negative 1 times negative 1, so it's still positive 1, 0. Oops, it's dotting. Let's try that again. It's 1 plus 0 plus 0, which of course is 1. And that makes sense because that's an outward pushing out of this thing. It's an outward dot product. We want that to be pushing outward. All right, so let's take a look then at F3. I'm sorry, S3. So if I look at S3, well, that's this face right here. It's in the positive y direction. And in this case, y is going to be held constant because y is always 1 here. So we're going to get that x equals x. Again, trivial parameterization. Y is always 1. And z is z. So if I do my function, the function is going to be x from up here, 2y, so that's really a 2, because 2 times 1 is 2, and then 3z. We're going to need f dot n Oh, I forgot to do n. Let's do n real quick. So our normal vector, in this case, let's see. Normal vector is actually just going to be, what, 0, 1, 0? Because what's going to happen is if you take the partial of these things with respect to x, that's going to be 1, 0, 0. If you take the partial of these things with respect to z, it's going to be 0, 1, 0, 0, 1. So basically what's going to happen is the only thing that's going to have a value is this middle one. You can go ahead and double check that. I'm not going to waste the time on doing the partials and everything here on this last video. So we've got f dot n, which is now going to give me 0 plus 2 plus 0. So f dot n is 2. And again, hopefully you can see, and I'm not going to write this whole one out, but S4, this is in the negative y direction. So the only thing that's going to really change here is that the function, instead of having a positive 2 here, is going to have a negative 2. So therefore our normal, which is also going to have it's going to be a negative 1 in here, going to have a negative 2 times a negative 1. These two are still going to be 0 when you dot them. So I'm still going to get f dot n equals 2. Again, that's really nice. Let's change up colors here. I'm going to bring S5 over here, which is really going to be our top of this thing. Or did I make S5 the bottom? No, I made S5 the top. Yeah, right here. So S5 is the top. Again, that's the positive z direction. So if you do all the process, again, I'm just going to kind of skip to this, and this should make sense, really. You really shouldn't even have to worry about doing the crosses. If you think about it, the positive z direction is straight up from this. That's where our normal vector is. So your normal vector should be 0, 0, 1. Unit vector in the positive z direction. And again, you would let your parameters for this would be x equals x, y equals y, and z would equal 1 if you wanted to write all that stuff out for this. We don't really need to in this case. So our function in this case would be x, 2y, and then 3 times z, which is just 3. So if I do f dot n, 0, 0, 3. Okay, and then once again, you should realize that S6, which is the bottom, is going to be exactly the same thing, because what you'll have is a normal vector 0, 0, negative 1, and this will be x, 2y, negative 3. So when you do f dot n, and I'm not writing it all out this time, you would still get 3. So now if we want to go ahead and integrate these things to be able to figure out our actual flux, now that we have f dot n, what you're doing, so let's go back to the idea of S1 here. So S1 is the double integral over S of f dot ds, which again, remember, we can write as the double integral over d of f dot n dA. Well, we've got all of our f dot n. Specifically for S1, f dot n was 1. So I'm taking the double integral over d of 1 dA. But what is dA? dA is the area of D. So it's the area of our domain. S1 has an area of this thing right here. Remember, this was from negative 1 to 1 in the x direction. I'm sorry, in the y direction. And then negative 1 to 1 in the z direction. So that's really a 2 times a 2. So the area of of our S1 section is 2 times 2, which is 4. So really what I get is 2 times 2 equals 4. Because I was summing up the area times 1 of 2 times 2, which is 4. S2 is going to be exactly the same as S1. And that's because they both have the same f dot n right here. So that's also going to be 4. S3, same idea, and you can see how this is probably going to go pretty quickly. The double integral over d of 2 this time, because S3 had f dot n, where is it? Right here, of 2. dA. And again, dA is going to be the same. This is a cube. dA is going to be the same for every single one of them. So it's really going to be 2 times another 4, which is 8. S4, same as S3. It's just on the other side. So we're also going to get 8. S5, if you recall, I'm not going to move it back up. It was the double integral. But we got 3 for our f dot n. And again, the top and the bottom have exactly the same dA. They have exactly the same area. So this is going to yield 3 times 4, which is 12. S6 is the same, I almost wrote an integral, as S5, which is 12. So our total flux, folks, nope, that's not it. Our total flux, outwardly oriented, is 4 plus 4 plus 8 plus 8 plus 12 plus 12. We get a grand total of 48. All right. Kept this thing to just a little bit under 18 minutes. So there we go. That is the rest of 16.7. You guys should be able to do the WebAssign now.